Okay, so let's jump right in here with the definition of binary operation. And I think you'll see pretty quickly that binary operations definition is doing exactly what things like addition and multiplication do, these things that you're familiar with. You know, addition and multiplication take two numbers as sort of an input, and then they produce a third number as an output. So 2 plus 3 equals 5. You combine 2 and 3 to get a third number, 5. So that's what we're trying to model here. So first of all, let's have a set from which our numbers or elements come. So S is a non-empty set. And a binary operation on S is then a function from S cross S to S. So notice that in this definition, the input values would come from S cross S. So technically speaking, the input values are ordered pairs, but really we're just kind of thinking we've got two elements, right? Now order is important because maybe when we do, S1 starred with S2, we get a different result if we turn it around and do S2 star S1. So the ordered pair part of it's important also, but we're kind of thinking of it as we've got two inputs, and that's captured by an ordered pair. And then the output value is just a single value in S. Whenever we want to put an ordered pair into this function, we usually write it this way. S1 star S2 indicates that we're plugging the ordered pair S1 comma S2 into the function star, which would be represented by this notation here. So that's what's really going on when we do S1 star S2. We're plugging the ordered pair S1 comma S2 into the function that we call star, and then S3 is the output value. But we usually just write that this way because it mimics how we write addition or multiplication, right? Even more cumbersome of a notation is we can think of star as a relation, because functions are relations, right? Which are collections of ordered pairs. So when you say S1 star S2 equals S3, the ordered pair that's in your relation is a funny looking ordered pair. The first component of that ordered pair is itself an ordered pair. And then the second component is just a single element from S. So anyway, we're going to probably use this notation most of the time unless we have some really good reason to switch to one of those other notations. So whenever we think about verifying that something is or is not a binary operation, it comes down to verifying this, that star is a function from S cross S to S. And when we use that notation, we know that it entails three things. The domain of the function star has to be S cross S, the range has to be contained in S, and then star has to have the function property. Let's talk about this a little bit and maybe interpret what we mean in each of these situations. So when we say domain of star is S cross S, the interpretation there is that any two elements of S can be starred. I know that's not a very technical term, but the idea is that you give me S1 and S2, I can do S1 star S2. That somehow makes sense. It's not some undefined operation. And then when we say the range of star is contained in S, the interpretation there is that for every S1 and S2 in S, then we see S1 star S2 is an element of S. So when you put the domain and range bit together, it just says any two elements can be starred, and the result will be an element of S. And then lastly, we have that star has the function property. We know what that means technically in terms of when we think of it in terms of this star being a function from S cross S to S. It means that whenever you have two ordered pairs that are equal in S cross S, and then you plug those into star, that you get equal results, which we have this notation for. We can think about this in a slightly easier way, because when those ordered pairs are equal, it means their corresponding components are equal. So we know S1 has to equal T1 here, and S2 has to equal T2. So maybe it would be slightly easier to say it this way. For every S1, S2, T1, and T2 in S, such that, let's say S1 equals T1 and S2 equals T2. So I'm just saying that those corresponding components of the ordered pairs are equal. Then it must be the case that S1 star S2 will equal T1 star T2. So S1 and T1 were equal here, and S2 and T2 were equal. And so we expect that when we star equal things that we get equal results. So you can kind of think of this as equals starred with equals are equal. Let's apply this to some things that are familiar and then some things that we'll contrive, but simple things. Let's start with some simple potential binary operations and think about why they satisfy our definition. So first of all, let's think about addition and multiplication, and we'll consider it on the integers, but everything that we'll say will be true of the rational numbers and the real numbers as well. So let's think about addition just for a second. What is the domain of addition? So what things can we add? Well, we know just from the axioms of the integers that we can add any two integers. So that means that the domain of addition would be z cross z, because we're going to add two things, right? So we got an ordered pair. So the domain of addition is z cross z, since any two integers can be added. The range of addition is a subset of z, since for every, let's say, m and n in the integers, m plus n is an integer. The axioms of integers are basically just assuming that addition is a binary operation. So it's assuming that you can add any two integers and that the result of which will be an integer also. And also, whenever when equals are added to equals, we get equals. For every, let's say, a, b, c, and d in the integers with a equal to b and c equal to d, we certainly have, if we do a plus c, that's going to be the same thing as b plus d, because a is equal to b here and c is equal to d here. We're just adding equals to equals, right? And all of this would be true for multiplication as well. So if you go back and replace addition with multiplication, everything holds true there too. But on the other hand, we notice that whenever you examine subtraction, well, subtraction definitely is a binary operation on all of the integers or all of the rational numbers or all of the reals, but it's not a binary operation on the natural numbers. So what breaks down whenever you try to think about subtraction on the natural numbers? Remember, the natural numbers are just the positive integers, right? Well, the problem is that you can subtract two integers and get a negative value, which would not be a natural number. Well, that's a problem with what? The domain, the range, or the function property? Well, it's the range, because we're getting an output value in the wrong place. It's not in the set we want it to be in. So for subtraction on the natural numbers, it fails the range property, i.e. the range of subtraction is not a subset of the natural numbers. But if you allow for all the integers, then you're good. So you got to allow those negative values. So here's a strange one. So we're defining a binary operation star on the rational numbers, and we take one fraction and star it with another fraction. We're going to do that according to this expression here. So you just add the numerators of the two fractions and then multiply the denominators to get the denominator of the result. So the question is this a binary operation? Well, let's just check the properties. So how about that domain? So just ask yourself, to get the domain, what fractions can I star together? Well, when I look at this formula, the only thing I'd be worried about is getting a 0 in the denominator, because certainly the numerator and the denominator are going to be integers. That's required for it to be a rational number. But I'm not worried about getting division by 0 here, because the denominator b and the denominator d are both not 0. So then this denominator over here is not going to be 0. So it looks like the domain is all of q cross q. So that's good. And similarly, whenever you look at the range of star, all of those outputs are rational numbers, because the numerator of this fraction is an integer, and also the denominator is a non-zero integer. We know that from axioms of integers. Then what I've got over here is a rational number. So it's an integer divided by an integer where the denominator is not equal to 0. So I know that the range is contained in Q, so that's good. How about the function property? Well, that's where this one breaks down. It fails the function property. So if you would take, I don't know, you don't have to be too exotic in what you make up. We know that 1/2 is equal to 2/4, and we know that like whatever 1/3 is equal to 2/6. So I want to star things like this. I want to star 1/2 with 1/3 and see what I get, and then I'm going to star 2/4 with 2/6 and see what I get. I should get the same answer because I'd be starring equals with equals if it's a binary operation, but I think I'm going to get different answers here. So if I do 1/2 star with 1/3, according to the formula, I would get 1 plus 1 divided by 6. But if I do 2/4 starred with 2/6, I'm going to get 2 plus 2 over 24. So this is 4/24 or 1/6, whereas the first answer I would just get 1/3, right? So 1/3 does not equal 1/6. So just like when we were checking ordinary functions have the function property, we have to be careful that the function's not sensitive to the form of the input. It has to really just care about the value of the input. So here we were using fractions, and the form of the fraction made a difference in the output value. So same sort of thing as we've seen before when thinking about functions. Okay, here's an example. Ooh, I'm using a new symbol for the binary operation. A circle with a dot in the middle. So define circle dot on the real numbers by x circle dot y equals the square root of x times y squared. So is this a binary operation? Well, when you see square roots and you're thinking about real numbers, you know you have to avoid getting negative numbers in the radical, right? Circle dot is not a binary operation because we can possibly get negatives inside the radical, but what specifically breaks? Is it a problem with the domain, or is it a problem with the range, or is it both? Well, since we're saying that we're defining this on R, then that's R cross R to R. So we're saying we've got a relation, we're defining a relation from R cross R to R. So the domain necessarily has to be a subset of R cross R, and then the range has to be here. So when I think about the domain of this thing, I can't consider any domain elements that will produce something that's not in R, right? So I don't know, these things are always a little bit, it's hard to decide whether it's a problem with the domain or a problem with the range sometimes. I think it doesn't really matter, it's just a point of view. So when I think about the domain of this thing though, if I'm requiring that the output values be real numbers, then I just won't consider anything as a domain value that will produce square roots of negative numbers. So I'm going to say that the domain here of circle dot does not equal R cross R because, for example, -1 circle dot 1 equals the square root of -1, and square root of -1 is not allowed since the range of star must be a subset of R. So if I sort of put my foot down and say I'm requiring that the range has to be a subset of R, then I get a problem with the domain. If I alternately, if I put my foot down and require that the domain is all of R cross R, then I'll have a problem with the range. So in examining these domain and range questions, it's always a matter of if you have a problem because you're trying to use all of your set, like R cross R in this case, and then that causes you to get outputs that are not in that set, R in this case, then you've got a range problem. Or if you just say, no, I'm not going to allow anything to fall outside of the codomain, then you get a domain problem. Okay, in the next example, we're defining a binary operation square on the rationals by A over B square C over D equals BD over AC. Now this one, we definitely have a domain problem because the numerators of those fractions could be 0. So I could say the domain of square is not Q cross Q because, for example, I can't do this. 0 over 1 square 2 over 3, that's undefined. So technically, what we're saying here is that the ordered pair is 0, 1, 2, 3, which is in Q cross Q, but that ordered pair 0 over 1, 2 over 3 is not in the domain of square. So that shows me that Q cross Q and domain of square are just not the same set because one set has an ordered pair that the other one does not. Here in fact 5.5, this just lists several common binary operations and just declares that each of them is a binary operation. The ones that involve ordinary arithmetic operations, addition, multiplication, subtraction, and division, are kind of difficult to prove without first having some rigorous definitions of what these things are, and especially when we do them on the reals or the rational numbers. So we're not going to try to prove these parts 1 through 7. Parts 8, 9, and 10 are not too hard to prove. These are just that union, intersection, and set difference are binary operations on the power set of any set. Those I'll leave as exercises. But we can use this fact to build up other binary operations. So I think that's what we'll use it for mainly. And it's important too. I mean, these are very common operations, right? We use them all the time. So knowing that they satisfy the conditions of a binary operation are important. So let's do a little skills check here. I've got a problem here with 3 parts, and I just want you to check whether or not each of these are binary operations. And then, if they're not, figure out why. And if they are, I want you to verify that it's true by checking the 3 conditions. So the first one is a star b equals a to the b on the natural numbers. And then the second one's just a variation of the first one. It looks like the same operation, but the underlying set is different. This time it's all of the integers instead of just the natural numbers. The third one is going to be a weird one. The set on which we're defining this operation is Z4. And remember, Z4 is a quotient space, so it's a set of equivalence classes with respect to congruence modulo 4 on the integers. So Z4, you can kind of think of it as, it's like 0 bar, 1 bar, 2 bar, and 3 bar. The 0 bar there is those are all of the integers that have a remainder of 0 when you divide by 4. So in other words, 0 bar is the set containing all the multiples of 4. And then 1 bar is the set containing all of the integers whose remainder is 1 when you divide by 4. And then you get the remainder 2 things and the remainder 3 things. And then we remember, like in Z4, 0 bar would be the same as 4 bar, would be the same as 8 bar, and so on. And like 1 bar would be the same as 5 bar, would be the same as 9 bar, etc. So that's what Z4 is. And we're defining this binary operation. So we take A bar and start with B bar. And it's a piecewise thing. So we look at A. If A is even, we're going to do A times B and then divide by 2. And then put a bar on top of that. So for example, if I did 2 bar star 3 bar, that would be 2 times 3 divided by 2 bar. Or in other words, that'd be 3 bar. But on the other hand, if the first term is odd, let's say if I did 1 bar star 3 bar, since that first thing is odd, I use the second formula up here. And so I would get 2 times 1 times 3 bar. So that's 6 bar. But then I would reduce that down to 2 bar because 6 bar is equal to 2 bar in Z mod 4. So that's how that function works. And so I want you to check whether or not it is a binary operation. So pause your video and give these a whirl. And then after you've had a chance to check them out, we'll work through them together. All right, welcome back. Let's look at part A. This one is a binary operation on the natural numbers. You can check the domain of star is going to be all of n cross n, because I can certainly take any natural number A and then raise it to a natural number power B, because that's just multiplying A times itself B times, right? So I can certainly do that on the natural numbers. There's nothing bad going to happen if I do that. And then, yes, the range of star here is contained in the natural numbers, because if I take a natural number, so that's just a positive integer, right? And then I raise it to a positive integer power, I'm just going to get a natural number. So I'm not going to end up with a fraction or anything because I'm not doing any negative exponents. So the range is fine. And then, yeah, it's certainly true that if let's say we got A, B, C, and D in the natural numbers, with A is equal to C and B is equal to D, then A star B, that's A to the B, according to the definition. But since A is equal to C and B is equal to D, this is certainly equal to C to the D, which is the same as C star D. So it satisfies the function property bit, so that's fine. Now, the reason I had you think about this same operation but on Z instead of the natural numbers is because you'll realize that it's not a binary operation on the integers. And the problem it has is a range problem. Range of star is not contained in Z since, for example, if I did 2 star negative 3, I would get 2 to the negative 3, which is 1/8. And so the output value there is not an integer. So the input values were integers, but the output value is not. And so when you use negative exponents in this thing, you get fractional values which are not integers, is the idea. So here I'm saying, okay, this is a range problem, right? Because I'm thinking, okay, the input values were fine. It produced, a perfectly good number. It just wasn't in the right set of numbers as an output value. Okay. Now C, this is the weird one. Okay, I'm making a copy of it here on a fresh page. So this one fails the function property, it turns out. Star is not a binary operation. It fails the function property. So for example, if I would do something like, I don't know, let me do 2 bar star 1 bar, because the first value that you're starring together here is even, then I would use the first formula there where I divide by 2. So this will give me 2 times 1 divided by 2 with a bar on top. So that's just 1 bar. On the other hand, if I would do 6 bar star 1, notice the corresponding components are equal. So again, the first component is even, so I do 6 times 1 divided by 2 with a bar on top. And so that's 3 bar, but we see that these two things are not equal. 1 bar does not equal 3 bar in Z4. So we starred equal things together in Z4, but we got different results. So it didn't have the function property. Although it had no problem at all with the domain and range. If you think about the domain, I could certainly star any 2 things together here could be starred, and the result would be an element of Z4. So no problem with domain and range. All right, so this next topic is related to binary operations. It's a topic that you use a lot in abstract algebra class, and so it's nice to get an introduction to it here in foundations class. I wouldn't say that permutations are centrally important to the idea of a binary operation, but they give us a setting in which the composition of functions can be thought of as a binary operation. And we know that composition of functions is important. And so giving composition of functions a setting where it can be thought of as a binary operation is kind of cool. So that's kind of what this is about. But it's also about, so permutations are really important in theory of probability, and they get used in abstract algebra a lot. And so getting you introduced to some notation involving permutations will be a goal here as well. So let's talk about a few definitions. So first of all, what is a permutation? So a permutation, all it is, well, we say a permutation of a set. You kind of think of a permutation as taking a set and shuffling it. Like if you have a 52 card deck, right? If you just shuffle that 52 card deck, the cards are still the same cards, they just end up in a different order. That's kind of what a permutation does, but we can think of that as just a bijection from the set to itself. So a permutation of a set A is just a bijection from the set A to the set A. I tend to think of that as just shuffling the set A. That analogy makes a lot more sense whenever the set A is a finite set, but it also, this definition applies to any old set, could be infinite or whatever. Now, if you start with a non-empty set and you look at all of the permutations of A, we give that set this notation script S of A. So script S of A is just the set of all functions from A to A that are bijections. So another way, we could have just said S of A is the set of all permutations of A. This set is called the permutation group on A. So when you get into abstract algebra, they use this word group a lot. So this is an example of a certain kind of mathematical structure called a group. But we're not going to be worried about that right now. It's just a name for now. So S of A is the permutation group on A. And we have one special case that we're going to focus on when we're thinking about permutation groups. Whenever the set A is just this finite set 1, 2, all the way up to n, just a finite set of integers starting at 1, we denote that by S sub n. So S sub n, that notation is reserved to indicate a permutation group of this finite set right here, 1, 2, 3, all the way up to n. So that's going to be our focus for the most part here, is we're going to be looking at S sub n, thinking about how composition works in there. But first, let's try to get a little bit of a handle on what we mean here. How do we describe these permutations in Sn? Well, for example, if I had something in S3, that means it's a bijection from the set 1, 2, 3 to the set 1, 2, 3. So for example, I could send 1 to 2 and 2 to 3 and 3 to 1. This would be an example of a permutation of the set 1, 2, 3. You can see that it's 1 to 1 and on 2. When you look at the range is 1, 2, 3. So that's all, that means it's on 2. And I don't see any repeated numbers over here. So it's 1 to 1. Similarly, if I say I want to have a permutation in S5, that means it's a bijection from 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5. So, I could do something like 3, 5, 2, 1, 4. This would be an example of a permutation in S5. Notice again, the range, if I look at the output values over here, I get 1, 2, 3, 4, 5. So it's on 2, and I don't see any repeated values. So it's 1 to 1. So it's a bijection. Even I could do one on S2. That one's really simple. There's not very many choices to have here. So I could have like 1 goes to 1 and 2 goes to 2. So again, I see the range is 1 and 2, so it's on 2. And I don't have any repeated values, so it's 1 to 1. So this is a way we could just describe permutations just by making a list of, where does 1 go, where does 2 go, where does 3 go, and so on. Another bit of notation I want to introduce down here is that I want to talk about the collection of all functions from A to A. So not just the bijections from A to A, but just any old function from A to A. We're going to indicate that with this cursive f of A, like this, sort of a script f of A. So script f of A is the set of all functions from A to A. That's it. So f doesn't have any special property like 1 to 1 or on 2 or bijection. It's just a function. So here in fact 5.7, we find out that composition of functions is a binary operation on f of A and s of A. And we're going to do the proof for f of A, and then to understand why it's true for s of A, it's just one additional comment needs to be observed. But let's go through this. Let's prove why is composition a binary operation on the set of all functions from A to A and also on the set of permutations of A. We need to prove the three things, right? We need to prove that if it's going to be a binary operation, then its domain would have to be all of f of A cross f of A. Its range would have to lie in f of A, and then it has to have the function property. So when equal functions are composed with equal functions, you get equal results. So let's do that. First of all, let's talk about why the domain of composition is all of f of A cross f of A. So like I said, we do composition on f of A, and then we'll talk about why it's true on s of A afterward. Why is this true? Well, we know just from the definition of composition, if we take two things, f and g, in f of A, then f composed with g would then be a function from A to A. See, we know f is going from A to A, and we know G is going from A to A. So when we compose those, it goes from A to A. And you can actually compose them in either order. You may not get the same result, but you can compose them in either order. So we also know G composed with F is a function from A to A. So let's just think of it this way. So any two functions in f of A can be composed. And then also the range needs to be a subset of f of A. We kind of already proved it. Given f and g in f of A, we have f composed with g goes from A to A. So f composed with g is, the result of composing them is also an element of f of A. So recapping what we've done so far, any two functions in f of A can be composed, and the result of which is also in f of A. So that answers the domain and range stuff. And so then the function property, so if you would suppose f equals h, well, let me say where these things live. So suppose f, g, h, and k are elements of f of A, and then we have some equal things. So let's suppose f equals h and g equals k. Now if we look at f composed with g, and let's put in a value x from A, according to our notational conventions that we use, this is the same as f of g of x, right? But g is equal to k, so that means g of x is equal to k of x. So this is equal to f of k of x, because g of x equals k of x, and f is a function, so it has the property that equal inputs give equal outputs. And then this is the same as h of k of x, and this is true, this is because f equals h. So if two functions are equal, they produce the same outputs when given the same input. And then this is just another way to say h composed with k of x. So this is true for x in A. So that tells you, according to one of the homework problems that we had worked previously on the chapter on functions, that if you have two functions and they produce the same output for every input, then those two functions are equal. So this tells me that f composed with g equals h composed with k. So we started with, equal. We showed that equals composed with equals are equals. Now that we know this is true for all of f of A, that's just all of the functions on A. The only thing to do it for s of A, that's the permutations. Well, the permutations are just or bijections, right? So if you go back through and you think about all this, if you compose two bijections, you get a bijection because we had a theorem that tells us back when we were doing compositions in the chapter on functions, we had a theorem that said the composition of two bijections is a bijection. So we know that, okay, we still know that we can compose any two bijections from A to A, so the domain would be okay. The range will benefit from that theorem that I was just talking about, because after I have composed two bijections from A to A, I get back a bijection from A to A. So the range part's okay. And then we'd get exactly the same argument for why it has the function property. So everything carries through for S of A also. The only part that really is even minorly different is, so we use the theorem, what was that theorem? So we would use theorem 4.28 to see that range of composition is a subset of S of A when we're doing the permutations. But everything else is exactly the same. So on the range part, we use that theorem to say that the composition of two bijections is in fact a bijection. So that's it. So that's the big sort of abstract result of this section. And now I just want to go and we'll do some very concrete things from here on out. We're going to talk about computing permutations in SN. So the rest of this section, the rest of this lecture is going to be very concrete and about computing things. So depending on your point of view, that might be a nice little break. So let's talk about two-row notation for permutations. So first of all, I think this is pretty natural. A permutation in SN can be represented as follows. So I've got this 2-row notation set up here, and I've got the top row of it is just the integers listed in order from 1 to n. And then just below that, I'm going to put what the function value is. So I'm going to put f of 1 here, f of 2 here, f of 3 here, and then f of n over here in the last spot. So this is telling me that the function maps 1 to this number, and 2 to this number, and 3 to this number, and so on. So for example, I've got g here, and I've got the top row set up as 1, 2, 3. And then maybe I do like 2, 3, 1 on the bottom row. So this is an element of S3 because it's only, it's a permutation of the set 1, 2, 3. And that 2-row notation here is telling me that 1 maps to 2, 2 maps to 3, and 3 maps to 1, right? So in other words, g of 1 is equal to 2, g of 2 is equal to 3, and g of 3 is equal to 1. In this 2-row notation, the only thing you got to worry about, the top row is fixed. The top row is always going to be the integer starting at 1 and going up to whatever your n value is. In order for it to be valid, you just got to make sure that the numbers in the bottom row, you don't see any repetitions. So in order for a 2-row representation of f and Sn to be valid, there must be no repeated values in the second row. So up here where I did g a second ago, if I had put 3 there, in this spot right here, well then I would see that g is not 1 to 1 because 2 maps to 3 and 3 maps to 3. I also see that it's not on 2 because 1 is not in the range. So having a repeated value really screws things up. So we got to make sure we don't have any repeated values. So let me put that back to a 1 there. With a 1 there, it is 1 to 1 and on 2. Permutations always have to be 1 to 1 and on 2. That's their defining property. So now we have this 2-row notation for representing our permutations. Let's talk about how we would compose them. So composition is our binary operation, and Sn is the set on which composition is a binary operation. So we want to play around with how that works. So in this example here, I've got f and g defined in 2-row notation, and I want to compute both of these compositions here, f composed with g and the reverse, g composed with f. So to do f composed with g, when you do composition, the function that's on the right is the first function, right? And then the one out here, the outer function, is the second thing you do. So if I do f composed with g, I find it helpful just to sort of line these things up vertically. Put g down first. 1, 2, 3, 4, 5, and then it goes 2, 3, 5, 1, 4. And then put f below that. 1, 2, 3, 4, 5. Try to line things up. 2, 1, 3, 5, 4, like so. And then f composed with g will be this. So first of all, I'll do 1, 2, 3, 4, 5. Okay, so I just track what 1 does. So first you put 1 into g, and you get an output of 2. Then you go to 2, and it goes to 1. So in the composition, 1 maps to 1. And similarly, I just track, okay, start with 2 in g. That goes to 3. And then 3, in turn, in f goes to 3. So 2 goes to 3 in the composition. 3 goes to 5, and then 5 in turn goes to 4. So I see 3 goes to 4. 4 goes to 1 in g, and then 1 in turn goes to 2 in f. So 4 goes to 2. I can guess where 5 has to go now, but let's just go ahead and track it. 5 goes to 4, and then 4 goes to 5. So 5 goes to 5 in the composition. See, by chasing those arrows, what I was doing, I was doing something like this, like f composed with g of 1. If I want to see where 1 goes in the composition, that's the same as f of g of 1, right? So first I said, okay, what's g of 1? Well, g of 1 is 1 goes to 2 there. And so then I'd get f of 2, right? So this is f of 2. And then I say, okay, now how do I do f of 2? So first I had that 1 was going to 2, and now I went to the 2. I'm looking at what happens when 2 goes into f, and I get back 1. And so that's how I got the 1 there. And similar reasoning goes for all the other values on the top row as well. And so yeah, we can do the reverse composition just the same way, but if I'm going to do g composed with f, in that order, f is going to be the function on top, and G will be the function on bottom. And so very similarly, okay, if I track things in F, 1 goes to 2, and then 2 goes to 3, so 1 goes to 3, 2 goes to 1 in F, and then 1 goes to 2, so 2 goes to 2, 3 goes to 3, 3 goes to 5, 4 goes to 5, 5 goes to 4, so 4 goes to 4, and 5 goes to 4, and 4 goes to 1, so we get 5 goes to 1, like that. So notice that G composed with F and F composed with G are not equal. In general, you don't expect composition to be a commutative operation. There are instances where F composed with G equals G composed with F, but in general, it's not a fact that you can switch the order as evidenced by this problem right here. Okay, now do you really have to, take up so much real estate on a piece of paper to get this? Not really. I mean, I could have just looked at the two things where they were written down originally in white there. If I was doing G composed with F in that order, where F is the first thing, then I could have just, 1 goes to 2 here, and then put that into G, and 2 goes to 3. So I can see if I do G composed with F, that I would get 1 goes to 3 in that composition, like I have at the bottom here. So, but maybe lining them up vertically like that helps initially. Okay, next thing, if we want to talk about inverses of permutations, it's really simple. So if I have my permutation here, just kind of written out in this sort of general form, we know that to do an inverse, all it does is it reverses the order, it reverses the components in the ordered pairs in the function. So that's just going to correspond to just swapping the rows on this 2-row notation. So F inverse would be like F of 1, F of 2, F of 3, ... F of M, and then 1, 2, 3, whatever in here. And then you want to reorder it so the top row is 1, 2, 3, ... in. Because after you've swapped it like that, the top row won't be in order, but it's our convention to put the top row in order, okay? Makes it a little easier to read the notation. So for example, just make up a quick example here. If F is equal to 1, 2, 3, 4, and then 2, 4, 1, 3, like so, then F inverse would be, okay, I can just swap it, right? So 2, 4, 1, 3, 1, 2, 3, 4, but then reorder 1, 2, 3, 4. Okay, so 1 was with 3, 2 was with 1, 3 was with 4, and 4 went to 2, like that. Now check it out. What do we expect to see when we do F composed with F inverse? What we expect to get is an identity function. We get a function that doesn't really do anything because they sort of cancel each other. If you track what F composed with F inverse does, so in this order, that means first do F inverse. So 1 would go to 3 in F inverse, and then 3 would go back to 1 in F. And so we see that 1 goes to 1. Similarly, we see in the inverse 2 goes to 1, and then in the original F 1 goes to 2. So 2 goes to 2. And then 3 is going to go to 3, and 4 is going to go to 4. So this is the identity function, or the identity permutation. So the identity permutation in general is just the function that sends x to x, right? 1 goes to 1, 2 goes to 2, 3 goes to 3, and so on. So here's an example. Given that F and that G, which are both elements in S5, let's just find this composition G composed with F inverse composed with G inverse. Here, maybe I'll just line these up vertically. Bear in mind, you do these things like the order goes from right to left when you're reading composition, right? Like you do the one that's on the right first, then you do the middle one, then you do the last one. So I'm going to write down G inverse first here. So G inverse. Okay. So 1, 2, 3, 4, 5. I'm going to skip a step of swapping the rows, and I'm just going to go, okay, after I swap the rows, 1's going to go to 1, 2's going to go to 3, 3's going to go to 2, 4 is going to go to 5, and 5 is going to go to 4 for G inverse. And then F inverse, if I reverse the arrows, I get 1 goes to 5, 2 goes to 3, 3 goes to 2, 4 goes to 4, and 5 goes to 1. And then I'll have G is the last thing we do. So I'm just going to write down a copy of G here. So now I can compose all these in the proper order just by following things from the top to the bottom. Okay, so 1 goes to 1, 1 goes to 5, 5 goes to 4. So in that total composition, 1 maps to 4. 2 goes to 3, 3 goes to 2, 2 goes to 3. So 2 ends up going to 3 in the composition. 3 goes to 2, 2 goes to 3, 3 goes to 2. So 3 maps to 2. 4 goes to 5, 5 goes to 1, 1 goes to 1. So 4 goes to 1, and then 5 goes to 4, 4 goes to 4, 4 goes to 5. So 5 maps to 5. Okay. So at this point, we're getting pretty good at, just taking compositions of permutations where we've expressed things in the 2-row notation. So now we want to introduce a new notation for permutations that's actually a bit more compact. What you see sometimes is that like elements map to themselves. And when elements map to themselves, like here we had 5 going to 5, we can kind of just suppress that in a way. So we can use something called cycle notation to kind of do away with the information that's just fixed. So let's talk about cycle notation. So before we get into cycle notation specifically, I just want to define this sort of exponentiation for composition. So if we have some function from a to a, then we can compose that function with itself, right? And we can compose it with itself 3 times or 4 times. And so by f to the k, that's going to be f composed with f composed with f, k times. So in the context of doing permutations, functions from a to a, and the operation is composition, in that context, the exponent's not going to mean multiply k times, but it's going to mean compose k times, okay? And now here's where we're going to do cycle notation. So first of all, the setup is that we have a1, a2, and ak are all distinct elements in 1 through n. So this is just a subset of 1 through n, okay? Now if those things are distinct, there's got to be less than or equal to n of them. So k is less than or equal to n here. And then now if we use this notation that f equals, so open parentheses, and then there's just a list. Notice that there are no commas either. It's just A1 and then space, and then A2 and space, and A3. So without any commas there, just spaces. What does this mean? So the idea is, so this is called cycle notation. It means that 1 goes to 2 when you put it into F. A1 goes to A2 when you put it into F. And in turn, A2 goes to A3 when you put it into F. And A3 is going to go to A4, and so on and so forth. And then the second to the last thing is going to go to AK. And then AK itself, what does it go to? It goes back to A1. So when you apply F each time, this is what F is doing on these numbers. You can see why it's called a cycle, because eventually it comes back around to the beginning number. So this means F of A1 equals A2. F of A2, which is the same thing as F squared of A1, because we're doing F and then doing F again. This gives you A3. And then you get A4, and then the second to the last thing in that list is AK minus 1. When you plug that into F, you get back AK, and then when you put AK back into F, that's when it cycles back around to the beginning, and you get A1. And then what about if this function F is going to be, maybe I should have mentioned it here. So this is going to be an element of Sn, okay? Maybe k was strictly less than n. So what about the values what about the values in 1 through n that were not present in the list A1 through AK? Well, all of those just map to themselves. So f of x equals x for every x in the whole set, 1, 2, all the way up to n, minus the set containing A1, A2, all the way up to AK. Defining cycles is kind of lengthy. This isn't the same way I defined it in the textbook. In the textbook, it's a bit more concise, but also not quite as clear as this. So I don't want to dwell on a precise definition too much, just because it just detracts from the idea, because the idea is not very hard to get. In fact, if I just give you one example, you probably have it, okay? So we know in this cycle notation from what we just said that F is going to have this effect. It's going to send 3 over to 2, and it's going to send 2 over to 7, and 7 over to 4, and it's going to send 4 back to 3. What about all the other numbers? See, this is in S8, So there's some other numbers that are not represented in that list of 4 there. There's like 1, you don't see 1 there, and you don't see 5, and you don't see 6, and you don't see 8. Those numbers just map to themselves. So it goes like this. So what we can deduce here is that f is equal to, let me do it in 2-row notation. Okay, so we got 1, I'm going to color code this a little bit, 2, 3, 4, 5, 6, 7, 8. Okay, now from the cycle notation, I can see where the ones in green go. 2 goes to 7 there, right? 3 goes to 2. 4 mapped to 3, and 7 went to 4. And then all the rest of the numbers just go to themselves. So 1 goes to 1, 5 goes to 5, 6 goes to 6, and 8 goes to 8, like that. So you see the advantage of this notation, right? This notation is a lot more compact of a way to express all that information. So by sort of, it's kind of a compression algorithm. You're taking all these ones that map to themselves and just sort of getting rid of that information. Like that's sort of a default that you don't need to write down. It's only the elements that move around that you keep track of. Okay, so now we can go backwards with this, like from the 2-row notation to the cycle notation. So check it out. So with G here in the second example, so I can just start a cycle and it's like start with 1. Take some element that moves. Like I wouldn't choose 6 because 6 doesn't move, right? The elements that don't move, they just aren't represented in the notation. So take something that moves, like 1 moves to 3, so I go 1 and then put 3 next to it. Then I see where 3 goes. Well, 3 goes to 4. Then I see where 4 goes. 4 goes to 5. Then I see where 5 goes. 5 goes to 2. Then I see where 2 goes. 2 goes to 1, but 1 was where we started, so this thing wraps off. And then, okay, so we used 5 of the numbers, and there are 2 others that we didn't use are both mapping to themselves. So we don't need to write anything. I suppose we could put if we wanted to put 6 like that and 7 like that to indicate that 6 just maps to 6 and 7 maps to 7, but I'm not going to bother. Now if we want to invert cycles, whenever we inverted 2-row notation, we just had to flip the rows, right? Well, when we invert cycles, so instead of reading from left to right, like so, we're going to reverse the arrows this way. So we're going to go 3 goes to 5, 5 goes to 1, 1 goes to 2, and then 2 goes to 3, like that. So F inverse would be, okay, so if I just reverse everything, doesn't matter which one you start on. Let's say you want to start with 1. If you start at 1 and you go backwards, it'd go 1 goes to 2, and then 2 goes to 3, and then 3 goes to 5, reading it backwards. But it doesn't matter which one you start with as long as you're consistent. Like if I put 5 first, that would be the same thing as, okay, 5 goes to 1 when you're reading the original backwards, which in turn goes to 2, which in turn goes to 3, which in turn comes back around to 5. So these representations aren't unique. You can't, in cycle notation, you can cyclically permute the entries of the cycle and you get the same function. So anyway, the upshot here is to find F inverse, just reverse the order of the cycle. Now one thing that needs to be pointed out here is that not every permutation is a cycle. I picked very specific examples that I knew were cycles. Like even this example G in the middle just looks like a standard 2-row permutation, but I cooked this one up specifically because I knew that it was actually a cycle. But not every permutation is a single cycle. So we need to talk about disjoint cycles and products of cycles. So the idea of disjoint is pretty straightforward. If you have F is like this cycle where you got A1, A2 up to AK, and you got G as a different cycle, B1, B2 up to BL, and they're both in Sn, okay? So they both are in the same underlying collection of permutations. So we'd say those are disjoint if that just means that the set A1, A2, all the way up to AK intersected with the set B1, B2, ... up to BK. Those 2 sets are disjoint, so the intersection is empty. So in the example right here, we can see that F and G are disjoint. because I can just compare the elements in each of those cycles, and I see that there's no common elements between those two cycles, right? So here is a good theorem. Whenever you have two disjoint cycles, so if F and G here are disjoint cycles, then in that particular case, F composed with G is equal to G composed with F. So we have this special situation. We know in general that F composed with G is not equal to G composed with F, but in this special situation, they are equal. So we say disjoint cycles commute, with respect to composition. So take these examples that we just looked up here a minute ago. So if we have F equals 2513 in S7, and also G is the cycle 4,6 in S7. So if we do, how can we verify that F composed with G equals G composed with F? Well, just convert it to a two-cycle thing. So what is F composed with G? That means first put things into G, and then put them into F to see what the output goes. Now these are in S7, so I got 1, 2, 3, 4, 5, 6, 7. I'm also going to do G composed with F in that order. Okay, so let's just see, what do we get? Now you got to think about this element by element. If I'm doing F composed with G over here on the side, and I put in 1, how would I track that where that goes? So that means to do F of G of 1, right? Now what is G of 1? I look at G here. 1's not present in that cycle, so that means G of 1 is equal to 1. So this would be F of 1. And then now I'm looking at F of 1, and I go, okay, where does 1 go in F? Well, 1 goes to 3. So in the composition, I just get 3. And so I get my first entry here, 1 goes to 3. And then I can similarly do 2. So I'm going to think about it this way. So over here in G, 2 goes to 2, and then 2 goes to 5. So 2 goes to 5 in the composition. Okay, starting at G again, 3 goes to 3, so nothing happens, and then 3 goes to 2. So we get 3 goes to 2 in the composition. Over here in G, 4 goes to 6. So now I'm looking at 6 over here in F. Now where does 6 go in F? Well, 6 goes to 6 because 6 is not listed in that cycle. 4 went to 6, and then 6 went to 6, so the output is 6 here. Okay, so now I go 5. 5 goes to 5, and then 5 goes to 1. So 5 maps to 1. In G, 6 maps to 4, and then 4 doesn't do anything in F. You get 4 there. And 7 goes to 7, just goes to 7 in both of them. And then you can do the same sort of reasoning, but in the reverse way. So when you do G composed with F, that means you first put things into F, and then take that output and put it into G. So starting with 1, 1 goes to 3, and then 3 goes nowhere. So 1 goes to 3. 2 goes to 5, and then 5 doesn't go anywhere, so 2 goes to 5. And if you follow this reasoning all the way through like that, you're going to get exactly the same result that we had up here. So the point is, these two things are equal now. Even though we composed them in different orders, they turned out to be the same. In the interest of time, I'm not going to prove this, but I do encourage you to look in the textbook for the proof. It's not super complicated, really. Oh, there's the example that I was planning to do. So now let's talk about products of cycles. So in the context of cycles in SN, when we use the word product, it just means composition. So instead of saying F composed with G, I'll just say FG, or F time. I may say F times G, but I understand that times here, when I say times, I really mean composition, okay? It's just a convention that people use in this context, okay? So in S7, instead of saying 2317 composed of 14, I'll just write that as 2317 times 14, and understand that times means composition here. So with that language in mind, here's the big theorem of this material. Every permutation can be expressed as a product of disjoint cycles. Now, I'm not going to prove this theorem either, but I'm just going to kind of show you how it sort of plays out. So let's look at this example F. Actually, the proof is very constructive. The proof is basically a recipe for how you would take a permutation and break it into a product of disjoint cycles. And when you're doing a product of disjoint cycles, remember, it doesn't make a difference what order you write things in, because we know that disjoint cycles commute. So let's look at F here. If I want to convert that to a product of cycles, just start anywhere. Okay, let's start with 1. Now 1 maps to 1, so that immediately wraps off. And I usually wouldn't even write that, okay? And I'm going to get rid of it in a minute. So then go to the next element you haven't used. So 2 goes to 4, 4 goes to 6, 6 goes to 7, 7 goes to 2. Oops, that means it wrapped off. So I already had 2 in the list, right? So this thing kind of wrapped around. So 2 went to 4, 4 went to 6, 6 went to 7, and then 7 wrapped back around to 2. Okay, now I haven't used 3 yet, so let's say this will be 3, and then 3 goes to 5, and 5 goes back to 3, so that wraps off. So at this point, I see that I've used all 7 numbers. So I would just write this as 2, 4, 6, 7, 3, 5. I would drop that 1. This would be my final answer. You see, all I did was just chase the elements where they map to in F, and then when it comes back to the same number you already used, you just wrap off that cycle. And you can check that these really are the same thing, right? And you can just check it element by element. If you look in the product of cycles, where does 1 map to? Well, you don't see 1, so 1 maps to 1, and that's exactly what happens in F, right? Where does 2 map to? 2 maps to 4, 2 maps to 4. Where does 3 map to? 3 maps to 5, doesn't it? 3 maps to 5, and so on. You can check that they do the same thing. But again, this is a lot more, the product of disjoint cycles is more compact, right? And then also, someone can hand you a product of cycles that are not disjoint, but you can still write that as a product of disjoint cycles. So this is just a composition of 2 cycles that happen to not be disjoint. How can we write that as a product of disjoint cycles? Well, it's very similar to what we just did with the previous example. So let me write this down here. 2, 4, 1, 3, 6, 4, 2, 7, 1, 5. Now the biggest number I see in all of this is 7, so I'm just going to assume that these are in S7. Okay, so here's how I can write this as a product of disjoint cycles. Start with 1. You got to start somewhere. And then we're going to figure out where 1 goes to in this composition. Now remember, you do compositions, you read right to left, right? So I'm going to start with the rightmost 1 that I see, which is here. Well, that 1 maps to 5. Now 5, I have to take that output and put it into the second cycle. But notice that there is no 5 there, so 5 just goes to 5. So 1 maps to 5 in this composition. And now let's see what happens to 5. I start with 5 in the rightmost cycle. It goes to 4. And then I see that, okay, 4 then in turn maps to 1. So in the composition, 5 maps to 1. So that means this cycle wraps off. Now let's pick a number we haven't used yet. I'll just start with 2. That would be the smallest number I haven't used yet. So what does 2 go to? 2 goes to 7. And then over here, 7 doesn't go anywhere, so 2 goes to 7. Okay, now what does 7 do? 7 goes to 1, and then 1 goes to 3, so 7 maps to 3. Okay, next, what does 3 do? 3 doesn't do anything over here, so 3 goes to 3, and then 3 goes to 6. So 3 goes to 6. Okay, next, where does 6 go? Well, 6 doesn't go anywhere in the first cycle, but then 6 maps to 2 here. So this thing wrapped off. 6 went to 2. Okay, what haven't I used yet? We got 1, 2, 3. I haven't used 4 yet. So I can see that 4 is going to have to map to itself, but let's just verify that. So 4 goes to 2, but then 2 in turn goes to 4, so 4 just goes to 4. But if it's ever a cycle of length 1, I don't need to bother writing that. I can just get rid of that. So this is it. So notice that this is a product of disjoint cycles. All right, now would be a great time to do a skills check. I've got a few just computations of these sorts of computations with permutations that I want you to do. So take a few minutes to do those, and then after you're done, unpause the video and we'll go through it together. Okay, welcome back. So for part A, I think we can just kind of do this by just sort of remembering that, you do composition from left to, or from right to left. So that means first do H, then do F inverse, then do G. So I know the result is going to be an element of S5. So I'm going to start off with 1, 2, 3, 4, 5 as the top row for this product. And then, so I'm just going to start with H and just sort of track where 1 goes. So in H, 1 goes to 5, right? Then I got to take 5 and put it into F inverse. So that just means to read F inverse backwards from bottom to top. So I put 5 into F inverse and it goes to 4. And then 4 in turn goes to 4 in G. So 1 ended up mapping to 4 like that. And then likewise 2 would go to 3. 3 would map up to 2 in F inverse. And then 2 would go to 3. So we see that 2 ended up mapping to 3. Okay, so next 3 goes to 4. 4 goes to 5 in F inverse, and then 5 goes to 1. So 3 goes to 1. 4 goes to 1 in H. 1 goes to 1 in F, and then 1 goes to 2 in G. So end up going 4 to 2. And lastly, although we could guess it by process of elimination that 5 has to go to 5, 5 goes to 2, 2 goes to 3, 3 goes to 5 as we expected. Okay, so that's the answer for part A. So for part B, to express G in the cycle notation, all you gotta do is just pick one of the elements that doesn't move. So I wouldn't start with 4, okay, so 4 doesn't move. So pick an element that does move. So let's say 1. I see 1 goes to 2. 2 in turn maps to 3 in G. 3 in turn maps to 5. 5 maps to 1, so I just wrap that off. And then 4 maps to 4. I mean, I could put that there like that, but there's no need. And then lastly, C. Okay, C wants us to express F as a product of disjoint cycles. So this is just like what we're doing in part B, actually. So pick an element that moves. So I don't want to do 1 because 1 just maps to itself in F. So let's start with 2. 2 goes to 3, but then 3 in turn maps to 2, so that wraps around. And then pick a number you haven't used yet, say 4. 4 goes to 5, and then 5 maps around to 4. So we see here we have disjoint cycles, right? 2 and 3, and then 4 and 5, those are disjoint cycles. Okay, the number 2, we want to write that as a product of disjoint cycles. Now one thing that might be pointed out is that this must be, I'm going to say this is an S9, this whole product, because 9 is the largest number that I see there. Although I suppose technically it could be an S100, where you'd have a whole lot of fixed elements. But let's just say this one's an S9. It wouldn't change the representation of it either way, though. So how does this work? So all you got to do is just pick an element. At this point, I can't tell what any of the fixed elements are, so I'm just going to start with 1. And then I'm just going to track it. Okay, so 1 maps to 9 in the rightmost map. 9 doesn't go anywhere in the middle map because there's no 9. Don't worry about the inverse for a second. We'll take care of that when time comes. And then 9 also doesn't go anywhere in this map, so 1 ends up mapping to 9. Next, let's see where 9 goes. Well, 9 goes to 3 in the rightmost map. 3 doesn't go anywhere in the middle map, and then 3 goes to 7 in the leftmost map, so 9 maps to 7. Now we'll track 7. 7 doesn't go anywhere in the rightmost map. 7, now because this is the inverse, 7 is going to map to 4, right? You just reverse the direction when you do the inverse. So 7 goes to 4, and then 4 doesn't go anywhere over here, so 7 maps to 4 in the total composition. Okay, now how about 4? So 4 goes to 2, 2 stays put, and then 2 goes to 3. So 4 goes to 3, 3 goes to 6, 6 stays put, 6 maps to 2. So 3 goes to 2, 2 goes to 1, 1 stays put, 1 goes to 5. So we get 2 goes to 5. Maybe we'll just get one big cycle. I don't know. I've already used 7 elements here. Okay, so 5 doesn't go anywhere. 5 doesn't go anywhere. 5 goes to 6. 6 goes to 4. 4 goes to 8, and then 8 stays put. So 6 maps to 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. I see that I've used all 9 elements, so it must be the case that 8 is going to map to 1, but let's just check to make sure that that's true. 8 maps to 8 here. 8, since we're doing the opposite arrow, 8 would go to 7, and then 7 goes to 1. So it did what I thought it would do. It wraps around. So I said to write this as a product of disjoint cycles, but if you only have one cycle, it's sort of vacuously true that it's a product of disjoint cycles because there's no other cycles to multiply by. It's just a single cycle. So this is the answer here. That works.